The diagram shows a uniform rod AB, 5 meters in length and of mass 20 kilograms, supported in a horizontal position by supports at A and C, where AC is 4 meters. We want to find the magnitude of the reaction at C. Here we have our rod, AB. We're told that it's a uniform rod, and the consequence of this is that its weight will act at the center. We're told the mass is 20 kilograms, so we have a weight, 20 G, acting at 2.5 meters from this end, which is halfway along the rod. Other forces acting will be a reaction force at A and a reaction force at C. We know that AC is 4 meters, so this must be 1 meter from B. We're now told that it's supported in a horizontal position. This implies that we are in an equilibrium situation, and an equilibrium situation suggests that the forces upward will be equal to the forces downward, and also that the anticlockwise moments will be equal to the clockwise moments. The moments must be equal whichever point we take our pivot about. Since we're interested in the magnitude of the reaction at C, a sensible place about which to take our moments is A. This means that we don't need to know the magnitude of the reaction at A, since its line of action goes through this pivot, and therefore it has no turning effect. So taking moments about A, we know that the anticlockwise and clockwise will be equal. This is a clockwise moment, and this one is an anticlockwise moment. So we have the 20G at a distance of 2.5 from the pivot, and this must be equal to RC, which we don't know, which is at a distance of 4 from the pivot. Rearranging gives us that RC is 20G times 2.5 divided by 4, and this calculates to give us that RC is 122.5 newtons. We're now asked, what is the largest mass that could be placed at B if the rod is to remain in equilibrium? If we place the mass at B, and since we don't know it, we'll call it M, and the weight will be mg. The weight of the rod acts at the center since we have a uniform rod. We have the reaction at A and the reaction at C. We also know in this problem that the rod is in equilibrium, but we're interested in when equilibrium will be broken. If mass m is large enough, this will pull down, which means the rod will leave the support at A. And if the rod is to leave the support at A, that means that the reaction at A will be 0 when this is on the point of happening. So the reaction at A is 0. If we take our pivot at C, the 20G will turn us in an anti-clockwise sense, and the mg in a clockwise sense. Since we're in equilibrium, these must be equal. We know these distances, and so we can work out the moments. The 20G times 1.5 must be equal to the mg times 1. The g's will cancel, and so we get 30 is equal to m, so the mass, the largest mass we can place at B, is 30 kilograms.